we do that separately?
No, that's an exercise.
Okay.
Yeah, I connected up 1, 2, and 3, and see if you can figure out 4. One connection with 4 is pretty easy, but the other one requires some work. Yeah, give me a holler, I can figure that out too. So, also, let me, Richard's actually giving a talk, my visitor's giving a talk on some stuff that'll be sort of related to this. He's gonna talk about almost second domains with norms, things like this. Might be interesting at 11:15 and where the ADM seminar is, which I've forgotten. I want to look it up. And also there's gonna be a math club talk on category 3. Sounds kind of exciting, so I encourage y'all to be there. Recall. So I want to talk more about data domains. I want to get some stuff organized here. I like this characterization. I and R, and actually it doesn't even really have to be an R, it can be a private ideal, is the vertical. If and only if there exists, let me say I 2 in R. I like this characterization quite a bit. An ideal is verbal if and only if you find some other ideal, you multiply them together, you get a principal ideal. I think we proved this already, and it's fairly easy to show. C I've talked about this ring in terms of, okay, it's ring about integers, then we'll talk about it in terms of being a dedicated domain. And here's sort of the first place I think that we can really see this, because C square root -5 is the integral closure. Of C in Q 5. So this has got all the little pieces, parts that we need. Okay? This is Z is a Dedekind domain, that's PID. Z is a Dedekind domain. This is a finite extension of the quotient field of Z, which is Q. Right? And this thing is the integral closure. And in fact, this was one of our homework exercises to show this. Finite extension, and we've shown in the homework that this is the integral closure. And so Z square root of -5 is integrally closed. Well, in fact, I don't even have to go through it. It's integrally closed in the theory and one-dimensional. But we actually have a theorem that any construction like this is dead, right? So, like I said, in the old days, it's bad factorization problems. And I'm going to show you sort of why for this ring this sort of has that. The classical bad factorization that you'd see in an algebra class is classical sort of thing. Um, this factorization doesn't look so bad to me anymore, when you think of this as ideals. In fact, in a certain sense, it's not. What happens in this ring is you have a principal ideal, then with the ideal generated by six. It can be factored into the principal ideal generated by two, the principal ideal generated by three, or into these other principal ideals. Right? These are all irreducible elements. We've gone through this kind of motion before. So these principal ideals here, 2, 3, and these two, are both maximal with respect to being principal. Let me show you why this kind of naturally has to come out of this. But let me find following prime ideals. Um, got that. Now, it turns out we've done this exercise before that we have P3 bar is equal to the ideal generated by three.
Everybody comfortable with that?
We've done this and, you get 4 generators, it turns out 3 divides them all, and you got 3 in. By the way, I've got a P3 and a P3 bar. Anybody know why I don't have a P2 bar? It's the same ideal, P2 bar. This is actually equal to. Because these two generators, their difference is 2, right? And so if you have this and this, you've got this. This does not hold in these two ideals. These are honestly different. These two are same. Same computation gives you this. P2 squared is the ideal generated by 2. So where do these come out? Well, this is going to be kind of an important concept and something we're going to look at. So I'm going to look at this example and then one like this that's got a little bit more meat on it. So if you look at the ideal generated by 6, think of this as a principal ideal. Well, this thing, Z joint square root negative 5 is a Dedekind domain. If all my theorems are right, which let's all hope they are, this should factor uniquely into prime ideals. And in fact, so this is, this is the ideal generated by 3. This is the ideal generated by 2, so okay, that makes sense, right? And you can actually, if you're an extremely patient person, you can sit down and write all the generators out and show this is the ideal generated by 6. I would do it in steps 2, just break it down like this. Notice that this is the ideal generated by 6. In a certain sense, this explains this because really, where do the other ones come from? Well, let's see what P3, P2 is. It's an ideal, but is it principal? Well, happens if you multiply these two ideals? Well, I don't know much, but I do know it will be generated by six. 3 plus 3 radical negative 5, 2 plus 2 radical negative 5. And then whatever this product is, which I guess is minus 4 plus 2 radical 5. 2 radical 5. Anybody want to venture a guess as to what this is?
Ideal generator, 1 plus.
That would be my guess. Check that, shall we? This one is not quite as clear on the containments. Let me kind of justify this one first. And let's hope that we're right too. Notice 1 plus radical 5 or radical negative 5 clearly divides this and this. I agree with that. And it divides this as well because of this factorization, right? So check window. This one perhaps not quite as clear, right? But let me do a little aside over here. I feel like I'm
From our generators there, don't we know that's just that squared?
Oh yeah, that's the easiest way to do this. I was gonna pretend that I was back in this actually, algebra 2 class in high school and minus 4, but yeah, Grant's right. I mean, that's kind of a smart way to do it. Is this divisible by 1? Does this turn out to be something in the right? And what would Miss actually tell me to do? Yeah, multiply that by the conjugate. So it's like that. And so this is going to end up with a denominator of 6. All right. And what happens in the numerator? Well, I get a negative 4. And then I get a negative 5, so that's plus 10. And then I get a plus 4 plus 2. And I'm feeling pretty good about this because this is 1 plus radical negative 5. And of course, if we had paid attention to Grant in the first place, we would see that that's what that turned out to be. Right. So this contains this. And I claim the other one. I claim that for the other containment, I need to somehow get 1 plus radical 5 in here. Anybody see how to do it?
Second generator minus 3.
Right, that'll do it, right? This is 3 times what I'm looking for and 2 times what I'm looking for. And there's a linear combination of 3 and 2 or the integers even that gives you 1. So yeah, and Adam saw the quick way, but this one is this. So actually what gets involved. So in fact, this horrible looking mess turns out to be much, right? So this turns out to be the ideal that. Oh dear, I've got to do another computation. What's a quick way to see what this one is? That's right. The conjugate of this ideal is this one. Because the conjugate of this is P3 bar, P2 bar, and P2 bar and P2 are the same. So this one right here is, mark this in green for conjugate. That. And notice, that's really kind of the only ways that you can combine them. Turns out that for this particular principal ideal, when I decompose it into prime ideals, I could put the prime ideals back in different ways, giving me different principal generators. Notice that it's interesting to see that, well, there was only 2 ways to do that. So when six factors into maximal principal generators, factors into two, 3 times 2. And the other way is 2 digits, right? Let's look at another example. Any questions on that? Look at another example. I kind of dig this one here. Let me recall for now for this. Yeah. R is containing domain. So I know it's an integral domain and every ideal is invertible. Then, by the way, you can define various objects in class groups for more general rings. Let's focus on this now. This is equal to we'll call this for you, where and by all invertible ideals, I mean all fractional invertible ideals, right? Because if you have an ordinary ideal inside the ring, it's inverse. The inverse ideal is not inside the ring if it's proper. And so notice that observation. If R is dedicated, then R is a UFD. If and only if R is by the way, if you think of Dedekind in terms of Noetherian, integrally closed, and one-dimensional or less, you actually need one of those. Yeah, so this sounds fancy. If R is Dedekind, then R is a UFD, if and only if R is a PID. But really all you need is for R to be what? Anybody remember? One dimension. It's one dimension. That's right. That's the important part of that here. It's for it to be one dimensional. And of course, notice that if the class group and this holds this, let's say R is UFD. If and only if because let's suppose that R is a principal ideal domain. That means that every ideal, invertible or not, is principal, which means that this is trivial. And on the other hand, if you have that this is trivial, that means that every invertible ideal is principal, right? And if you're Dedekind, then every ideal is invertible. Therefore, every ideal is principal, right? Everybody okay with it? So this little gadget we're going to start to put under the lens a little bit more is sort of measuring, in a certain sense, how bad your factorization can screw it up. Like if you have a trivial class group, great, everything's unique. As you move away to more complicated, class groups, you can have more complicated things. Or more complicated factorizations. So I'm gonna give you kind of this is a spoiler, so a little bit. It turns out that CL C squared root negative 5 is isomorphic Z mod 2Z. That's, in a certain sense, that's as small as you can ever be without being trivial, right? It turned out that when I factored 6 as elements, 3 times 2, 1 plus radical negative 5, 1 minus radical 5, 2 factors. This is not a coincidence, right? I mean, I only factored 6, but it turns out in this particular ring, any 2 factorizations of the same non-zero non-unit actually all have the same length. So you might be able to factor it a whole bazillion different ways, but every time you refactor it, it'll be the same length of factorization. And that's because of this class group. And I'll prove the theorem about that later. Before that, let me give you a more exotic example. So, let's see if we can come up with factorization here that's a little bit more interesting. Anybody, so I want to come up actually with factorization of something in here that's a little bit more exotic, that has factorizations of different ones. And it might be useful to use, again, the norm. If you have the norm of some element, I find if I spot something. This normal was very fast. Let me point out that if I let A equal 5, B equals 2, that's 25 and 56 is 81. And 81's got a lot of factors, right? It's 4 power. Right? So this means now this is the beginning of a good idea, perhaps. But I want to know what my irreducibles are, right? Because how do I know? I mean, 3, how do I know I can't break that down? How do I know this one's the big one? How do I know I can't break this one down? Let me make a couple of claims. 3 is irreducible. And C. Right, that's exactly right. Because I suppose And so to be interesting, you'd have to have. Because the only divisors of 9 are 1, 3, and 9. If your divisor is 1, then that's a unit, so boring city. If your divisor is 9, then the other one has a norm 1, boring city. So the only way this will break down in an interesting way is the norm is 3, and this is a contradiction. Because even with my bad skills, I can tell that there's no way you can write 3 as a square plus 14 times a square. Right, because if B is 0, you can't do it, and if B is 1, it's too big. Right, I love imaginary quadratic fields, right, they've been quite easy. Okay, here's one that will a little more juice to it. Okay. Well, let's try the same thing. Well, it can mean that 81, which is the norm of this thing, is norm alpha, norm beta. And now I see I'm not off the hook so easy because I got a lot of choices. All right. So for non-trivial factorization, need norm alpha to take on the values 3. Well, actually, let me list all the values that it can take on. Right, because the norm of alpha has to divide 81, so it's got to be a power of 3, right? 1, well, we could throw that out because that would mean it's a unit. And 81, we could throw it out because that means the other one's a unit. 3, we can throw out because of our previous argument, which means we can also throw out 27, because if the norm of alpha is 27, the norm of beta has to be 3, and we know that can't happen, right? So what must happen is the norm of alpha must be 9. That's it, right? And so the only way to represent 9 as a square equals 14 times a square, first of all, it's immediate that you have to have y equals 0, and that means that x equals plus minus 3 and y equals 0, so alpha is plus or minus 3, and that's a contradiction, because even I can tell that 3 does not divide this, right? So this is an honest to goodness irreducible factorization. So we have let's say R irreducible factorizations. Here you've got 1.2 and 1.4. But of course, the ones that link 2 have big fat norms, and the ones that link 4 are more economic, right? How could I do that? Right? I mean, what happened here? It's different. Right? Oh, by the way, we'll talk about this later, but the elasticity of this factorization is at least 2. Right? What do I mean by elasticity of a factorization? Well, I'm going to make this more formal later, but you take an element and you factor it all the ways to the factor. Right? For every factorization, take the long divided by the short length. Right? So look at all possible long lengths by all possible short lengths, take the supremum over that, and that's the elasticity. It basically measures how different the factorizations can be. it turns out that this is an extreme case here. And so this particular element has elasticity, too. What happens here that's different? Why can I build these things like this? Well, it turns out. So I'm gonna do some computation. I'm gonna prove this, but I'm gonna give you some heuristic evidence that can show you how this works. It turns out that CL oh, wait, you might know what this one is? So small. It is. Let me state my notation here. And let me show you that at least it contains it. So it turns out I'll often write these classes additively, but I'm gonna write them here. So this, if you believe me here, this is thick with group forward. So in this class group, there should be a class of order 1. That's the principal class, right? Those are the ones that are the cosets that are just principal. You should have a non-principal class of order 4, another one of order 4, it's inverse, and then that one in the middle, a square of order 2. I'm going to give you a representative in each class. How about the ideal general dog line? Right, that's certainly responding. The class A is 3 plus A squared plus A cubed. So you're taking a little bit of this on faith right now, but this is the principal class. Every fractional ideal that's principal is in this class. You got another class that corresponds to this ideal. All right, this is non-principal, and I'm going to show you that this is 4 or 4. This is a non-principal class of order 2. You square this one, you should get principal. This one's actually fairly easy to see. And this one is just the conjugate of this, so it's the inverse, right? Let me do some computations to kind of put this on better footing. Thing first, 2 radical negative 14 squared is principal. Well, let's look at this. 2 radical negative 14 squared is 4. 2 radical negative 14 generated by those 3 elements, right? It is clear, is it not? The ideal generated by 2, which is the principal ideal, contains it. And it's also clear that 2 is contained in it. Because if I have let's see, minus this, minus 3 times this, I get 2. Right. So that's fairly easy to see. Claim. This is going to be generated by 3. I claim the product of these 2 principal comes to the other end as well. Let's see this. This multiplies out to 9, 3 plus 3 radical negative 14, 3 minus 3 radical negative 14, and then 15. Right? Yeah, it's clear that 3 contains these. And if you look at 9 and 15, their greatest common divisor is 3. And so 3 has to be in. Okay, now, y is this of, order 4. Right. This was kind of yucky.
So that one of them squared. The other. That's.
Well, okay, I mean, I certainly don't want to take the fourth power of this. When I square this out, it's gonna be kind of a mess, alright? Well, let me just square it, see what happens. Um, square it first. Well, this is going to be 9, 3 plus 3 radical negative 14. And of course, to the square of this, which is minus 13, 2 radical negative. So, but okay, so I guess we could square this as well. Oh, yeah. What do you suppose we get? Anybody want to guess? Get the square this again? Five plus 2. Well, let's see if we can predict what's gonna happen.
Why don't we just do like a times a squared, show that that's a cubed, and then our result follows from the competition.
Well, that's right, that's another thing. We could do a times a squared, right? And then what we would have to do is verify that that's in here, so that's another thing, right? So you'd have the idea of doing by 6, 3 radical negative 14, which is quite easier. This thing right here, and but see, here's the problem. A times a squared will not equal this, but it'll be something equivalent to it.
Yeah, you get 6, 2 minus square root minus 14, and that's when you divide that by 2.
Okay, good, we'll do that.
Or
But
2 minus 2.
let me come back to this idea. I'll come back to this idea in a second, though. I want to see how the elemental factorization. So I like that idea. Let's do this. 3, 1 plus radical negative 14. So this is the one looking A, and 2 radical negative 14. So that might be a little bit less obnoxious to multiply out. If you multiply these, you get 6, 3 3 radical negative 14. 2 plus 2 radical negative 14. And then minus 14. Plus radical negative 14. Yes. Okay, so how do we shortcut this one down? All right, so notice that, let's see, I wonder if I can get it lower here. This should be an ideal actually norm 6. So what we want to do actually is show that it is equivalent. So it's in the same class as this. So there's some principal ideal that you multiply this and get this. Anybody see what to do?
You subtract 3 square root minus 4, or if you do 2 plus 2 square root minus 14 minus 3 square root minus 14, you get
Yeah, you get 2 minus square root of minus 14. You add it to that, you get minus 12, but that's breaking this plus 6.
Trying to reduce, so like aesthetic times. Or it's not the right number, so you can always reduce it down to 2 generations.
Well, that's right. The theorem that I gave you last time, this should be generated by 2 elements. Right? I mean, anybody see what 2 elements we can use? And unfortunately, 2 elements may not be any of these that are listed. They might be, it might be some crazy linear combination of them. Let's see here. My guess is 6, so it's 2 and 3. You might be able to use this one.
Get rid of this, the third.
Yeah, I think you can get rid of the third one because if you look at
Simplify it by getting rid of all of the, reducing the integer part on 6 and.
right, so you can certainly change the sign of this one, right?
what you can do is you can do 2 times 6 and add that to, well, what you had was minus 14 plus square root.
Subtract
Minus 14
12
from
from
that.
that.
So you get, yeah, 2 2 plus 6 square root minus 14
Add
and
the
yeah.
Okay, so where are we at now? So we've got what, 6? And
3 root negative 13.
or negative 14.
then 2 minus.
Like that. Just down to that. Okay, can we go further? Well, notice if you have 3 times this, right? And you subtract the 6 off and you get this. Right, so this one you've got using just these 2, right? Agree with me? So actually you can generate this by 6 and 2 minus radical minus 14. Okay with it? And that looks right. Now the question is, doesn't look like this, does it? No, it doesn't, but it needs to vary by principal ideal. So does anybody see how you can vary these by principal ideal? Are you guys sure that we didn't have? It should be 2
Might have
minus.
screwed up somewhere.
Yeah, I think this is actually supposed to be minus 2.
Because if you subtract the 12 away from the 14.
Okay, let's go back and be more careful. I think I did make a slip. Okay, so let's reduce first. We're gonna leave the 6. And we're trying to get rid of one of these, right? So, we're gonna have, or try to write one of these linear combination of the others. So, right, I'm willing to bet that you can put these together and make this one. That would be my guess here.
Or I guess you can also put the other 3 together to make the last one.
Yeah.
And so you can keep the 2 plus 2 radical.
Well, we could do that. Let's make sure about that. How do you put these together to make the last one? Minus this, plus this, that gets you a 2, and then the 6 gets you 14. Okay with that?
But now we can cancel the 3 for negative 14.
Well, that's what I think that's gonna be all right, because I think we're gonna have to change this. Now, okay, so is everybody okay with this? Well, just subtract this one from this, and you get this.
Yeah, one on.
That's
I mean, minus
plus 2.
negative 14.
Oh, minus.
Yeah.
Yeah, just minus one. So we were right about this. Let's see, let me make sure we didn't miss a sign. Minus this plus this, that gets to minus 14. And then we got 2, and then 2 of these, yeah. So that was correct. Then I can subtract this off, and this is where we were before. Now we can get rid of the 3 radical negative 14, all right? So I guess that was right. Everybody have this. Now, the question is, how do we relate these two? Because if this computation is correct, then this must be this. Anybody know how to verify it? Notice 3, 1 radical negative 14 times 3, 1 plus radical negative 14. So in other words, this thing right here functions as an inverse to this thing, right? If these two are in the class, then it must be the case then 3, 1 plus radical negative 14 times this thing we got should be principal. Right, because basically in the class group, in that quotient group, these two things are supposed to be equal, so they should have the same inverse. So the test is to see if it's principal. And this right here is 18, 6 minus 3 radical negative 14. This is 6 plus 6 radical negative 14. And this is 2 plus 14 is 16, plus radical negative 14. Assuming that I did that right. And so what's the outcome here? This should be something of norm 3, 2, 3. So it should be a norm. Yeah, it should be something like that. It should be 2.
That's the second
Uh,
If that's it.
yeah, it's a good bet. It's the second one. So here's your exercise for next time. So check me on this, right? Because if you don't find that the second one divides all these, then we messed up, which would not be a huge shock. But I think you probably got it right. Check that for next time, and And we'll kind of pick up and we'll talk about the class structure. Any questions? Well, I hope to see y'all at the math club. Y'all have a